get into it. Okay, so I wanted to show you guys another proof of the fundamental theorem of calculus part 2. So this is proof number 2. And this proof is a little bit different. So just a reminder, we've got A equal to x naught, and then x1 is, and the next one, x2. Eventually you get over to, x sub n minus 1, xn equal to b, right? The graph of the function is whatever it is, and so we're trying to find the area bounded from A to B, right? And so our goal, of course I should remind, delta x is b minus a over n, and the ith interval, ith point up here is defined by a plus I times delta x, right? Okay. And we're going to, so this is the graph y equals f of x, right? And our goal is to calculate the integral from a to b of f of x dx, essentially, right? We want to show that that's equal to f of b minus f of a. All right, where what? Where f prime of x is equal to little f, right? So big F is an antiderivative of the integrand, which we're trying to find the area bounded by, the graph of the integrand. Now, FTC I proved for us that there exists an antiderivative if little f is continuous, right? And that antiderivative is the area function. But for the purposes of this proof, I'm just going to assume, all right, that there exists f such that f prime of x is equal to f of x for all, a less than or equal to x less than or equal to b. So I'm assuming that the antiderivative of little f exists, all right? It's big F, and what can you tell me about big F? So since f prime of x equals little f of x on AB, we find f is both continuous and, on AB and differentiable on, of course, the open interval from A to B, because if it's differentiable, it's differentiable on A comma B. What this means then, right? So if you have a function which is continuous and on the closed interval, differentiable on the open interval, you can do what? So likewise, f is continuous and differentiable on the interval x sub I minus 1 to x sub I, right? So let me just kind of illustrate it over here. If we look at the first interval, right? Like here, the antiderivative is differentiable and continuous there, so we can apply the mean value theorem, right? And what does the mean value theorem say? It says that, there's some point the mean value theorem, there exists, let's say, x sub I star, which is an element of the ith subinterval, such that what? Such that f prime of x sub I is equal to big F of x sub I minus big F of x sub I minus 1, divided by what? Divided by x sub I minus x sub I minus 1. But what does that say? That says, remember, big F is the antiderivative of little f, right? So what's big F prime? It's f of xi. F of xi star is equal to big F of xi minus f of xi minus 1 divided by, what's the difference of the ith and the I minus 1 partition point, remember? It's essentially, by construction, just delta x, right? So the denominator here is delta x. What does this say? This says that f of x sub I star delta x is equal to f of x sub I minus f of x sub I minus 1. So what I'm proposing is that we choose the sample points in the Riemann integral using the mean value theorem applied to the antiderivative on each subinterval. So like, the Riemann sum would be the sum I equals 1 to n of f of x sub I star delta x. Now, I need to take the limit as n goes to infinity to actually calculate the integral, right? But check it out. So what is this? This is the sum I equals 1 to n of f of x sub I minus f of x I minus 1 by this calculation over here. I don't know if you guys have ever seen a summation like this before, but something really neat happens. Can I write it out? Let me write it out. We'll start with I equals 1. What is I equals 1? I equals 1 gives us f of x1 minus f of x naught, yeah? There's I equals 1. I equals 2, f of x2 minus f of x1. All right? What do you write next? Well, so forth and so on, right? So the next one would be f of x3 minus f of x2. And it keeps going. Eventually you get to f of xn minus 1 minus f of xn minus 2. And then finally the last one, f of xn minus f of xn minus 1. So like the last term I wrote, this was I equals to n. This was I equals to n minus 1. This was I equals to 3. This was I equals to 2. This was I equals to 1, okay? you guys see anything happening here? You guys ever seen one of those like old-timey telescopes that is like, you know, it collapses down? So this is what's called a telescoping sum because it kind of just, see, check it out. This guy and that one, they cancel, right? This and this cancel, right? There's an x2 that would be there if I kept writing that cancels the, I mean, there's an x3 and the next thing I haven't written which cancels.
So would you eventually just get an F initial plus F final?
Something like that. So this guy cancels with this guy, right? And this one cancels with something I haven't written here. So you're right, there's only two things that remain. Just two things. This one. And this one. But what are those? That's minus f of A plus f of B. So of course, if we take the limit integral from a to b of f of x dx, the limit as n goes to infinity of the Riemann sum, well, that's the limit. This limit's kind of easy to take, you know. F of b minus f of a by my calculation, right? So it's f of b minus f of a. So this is a rather different proof of the FTC II. Like the way we proved FTC II last class was, you know, far more elegant. But I like this proof because it does give you some sense of why it is that only the endpoints matter. It's really weird that the area is completely determined by the values of the antiderivative at the end and at the beginning subtracted, isn't it? Like, why doesn't the area of the function depend more on what happens in between a and b? Why does the formula just involve a and b? What about everything in between? Well, somehow those things cancel out, you know? But anyway, there you go. Okay, so next up, I need to share with you FTC III. All right, so what is the fundamental theorem of calculus part 3? Let me just kind of give you a quick derivation of it. It's not that complicated, really, the idea of it. I mean, if I was going to be fussy about the analysis, it might be pretty hard, but we're not that fussy in here. So here it is. We know that the integral from a to b, right, of f of t dt is big F of b minus big F of a, right? This is what I just proved, right? So if both a and b are functions of x, then we can differentiate the above. So we have d dx of the integral from a to b of f of t dt, yeah, equals d dt of f of b minus d dt of f of a. And so we're differentiating a composite function in both cases, right? How do you differentiate a composite function? Well, a chain rule, right? So this is f prime of the inside function b times db. Did I write t? I meant to write x there. Goodness gracious. X. Huh. So db dx minus f prime of a times dA dx by the chain rule, right? But what are we assuming about f? That f prime, big F prime, is equal to little f, right? That's our assumption in this whole discussion. Big F is an antiderivative of little f. So what are we looking at here? We're looking at little f of b times dB dx minus little f of a times dA dx. So this result right here, that the derivative of an integral with variable bounds, that this is equal to that, I call this FTC III. As far as I know, I'm the only person who does this. I just think it's useful to have it stated as a theorem. Typically, books kind of like half say it and then give homework problems on it that are really not explained by the text. So I'd rather just state a theorem clearly and let you guys use it. So you see FTC III becomes FTC I in what case? If A equals to constant, right? And B is equal to X, then FTC III becomes FTC I. Because you just get this reduces to what? Like that's 0, because the constant derivative constant 0, and this is 1, so you just get f of x, which is what FTC I said. FTC I said d dx integral from a to x of f of t dt equals to f of x. Okay, that's FTC I. So this becomes that in the case that, b equals x, dB dx equals to 1, a and dA dx equal to 0. You could look at FTC III as a special case of FTC I if you want. But anyway, as you may recall from last class, it took us a little work to prove FTC I, right? It took some time. It wasn't entirely trivial. In fact, it's probably the most sophisticated argument I've shown you this semester, as far as I can think of. So any questions? Let's look at 3 examples of this. d dx of the integral from x squared to x cubed of the square root of 3 plus 1 over x, rather t, dt. So identify here little f of t is what? So we're going to do f of x cubed times 3x squared, right? Minus f of x squared times the derivative of x squared, which is 2x. This is just a parenthetical comment here. So that's 3x squared times the square root of 3 plus 1 over x squared minus 2x square root of 3 plus 1 over, did I say x squared there? I'm an idiot. So you guys tell me which one of these is wrong. See up here? F of x cubed. I'm supposed to plug in x cubed in the place of t. But I put a square there, right? So that's supposed to be x cubed. Me neither. But I'm going to close the door. Any questions about this? Example 2. d dx of the integral from, let's say, inverse tangent of x to e to the x of the sine squared of x squared plus 2. And I should have said t squared, sorry, t squared plus 2 dt. So like identify this right here is my quote unquote f of t, right? So I'll just get straight to it here. We've got sine squared of, fine, I'll write the in-between step. Why not? Why not? I'm supposed to have f of e to the x times the derivative of e to the x, which is what? E to the x, minus f of inverse tangent of x. What's the derivative of inverse tangent of x? It's 1 over 1 plus x squared, right? So this is by this is, again, by FTC III. This is by FTC III. Sorry, I'm getting lazy not writing that. My bad. Okay, so I do sine squared. And I replace t with e to the x, so I get e to the 2x plus 2, all times e to the x. That's the first term. So what I did there, of course, was e to the x squared is what? That's e to the 2x, yeah? So I plugged in t equals e to the x. Now I'm going to plug in t equals inverse tangent of x. So I do sine squared of inverse tangent of x quantity squared plus 2. All divided by, if you like, 1 plus x squared. There you go. Didn't I just shut the door? Did I shut the door and then go back and open it again? I have no memory of doing that. Whoa.
Getting closer and closer to Halloween.
Man. I keep leaving stuff after I'm about to leave, and then I get talking to a student, and then like I just leave stuff in the classroom. And thankfully somebody else, another teacher, like just keeps bringing it back to my office, but it's just the principle of the thing. It's kind of disturbing. All right, one more example of these. The derivative with respect to x of the integral from 2 to the x to 3 to the x of the cube root of 1 plus the square root of t dt. There we go. All right, so I'm just going to go ahead and just do it. So I take, first of all, the cube root of 1 plus the square root of the upper bound function, which is 3 to the x. I take that and I multiply by the derivative of 3 to the x, which is natural log of 3 times 3 to the x. And then I subtract the cube root of 1 plus the square root of the lower bound, which in this case is 2 to the x. And then I multiply by the derivative of 2 to the x, which is natural log of 2 times 2 to the x. And this is, of course, by FTC III. And there you have it. Hooray! Why did I open that door? Oh, maybe I didn't open it. Maybe I just didn't latch it, and then it opened itself. It's actually got a strong opening thing. Total change theorem. Check this out. So if we integrate from x1 to x2, dy dx dx, what do we get? What happens if you integrate a derivative? So what's the antiderivative of dy dx? In other words, d dx of what is equal to dy dx? Mm-mm. Just y. Y. Y is what you differentiate to get dy dx. I know it seems too simple, but that's it. So this is y of x evaluated from x1 to x2 by FTC II. Right? So here, of course, we're assuming that y is itself like, a differentiable function apparently, right? And anyway, so what is that? Well, that's y of x2 minus y of x1. So this right here is what you might call the change in y over the interval x1 to x2, right? And so this is the total change theorem. Oftentimes, we use independent variable t instead of x if we actually want to think about a time rate of change. I'll give you an example. If dy dt equals to, 2t plus 1 is the number of cats thrown out window per unit time. Well, let's say per hour. So we're supposed that t is in hours and y is in cats. And if I wanted to know, how many cats were thrown out the window, say from hour 1 to hour 2, then I would integrate from 1 to 2 dy dt, right? Then the total change theorem would tell me that that's going to give me the change in y that I'm interested in. All right. But on the flip side, I can calculate it, right? Because I know that dy dt is given to me to be 2t plus 1, right? And we know how to do integrals now. So we do what? FTC II. What's the antiderivative of 2t plus 1? It's 1/2 t squared times 2, right? So the 1/2 and the 2 cancel. So you get t squared for the first thing, right? Very good. What's the antiderivative of 1? X, but here, since we're working with t, we put t, yeah. But, I mean, right idea, just wrong letter. Okay, so we have to sometimes adjust our thinking to the letter at play, independent variable here being t. And then, of course, we take that expression and we evaluate it from 1 to 2. And so that is 2 squared plus 2, parentheses, minus 1 squared plus 1. So apparently the number of cats thrown out the window was 4 plus 2, 6, 6 minus 2, 4 cats. Okay, so that's a start. There might still be more cats to throw out, I don't know, but there you go. You guys ever seen UHF? UHF. UHF is from 1988. This is Weird Al Yankovic's masterpiece.
See, now I'm seeing Weird Al Yankovic, but I've never seen it.
Right, this is a movie he made in 1988, which has parodies of like big 80s movies, like ranging from Gandhi to Conan the Barbarian to Rambo to like Raiders of the Lost Ark. And then just mountains of just wall-to-wall goofiness and other things. It parodies like, I don't know, 15 different movies, but it does have a coherent story. One of the major actors in that is the guy who played Kramer on Seinfeld. It's Michael Richards. He's like the major character in this as well. And it has other people you might recognize as well. I don't know. It is one of my absolute favorite movies. I could quote you many, many things from this movie. But there's a particular scene in that movie. So the movie's based on like a TV station, and they have all kinds of bizarre shows that they put on to keep the TV station on air. One of the shows features an animal trainer who's teaching poodles how to fly. And so he's just like throwing poodles, a small dog, You know poodle?
Huh?
You know poodle?
Yeah.
Okay. I mean, that seems like a word that could get lost. I could totally see like a non-English person who's not English as first language, like never.
It's the same word in Swedish also.
Oh, really? Oh. Oh, okay. But he's just throwing poodles out the window. It's one after the other, trying to teach them to fly. It's just, I mean, you have to watch it. You have to watch it.
Like just out of one story? Or?
No, a second story. And then later, they come out, there's like an outside shot, and you can see a literal pile of poodles outside where he's been throwing them. It's an amazing movie. It did not get recognized. Unfortunately, this movie came out in the shadow of the Batman movie, which was very, very successful for its time. They're like the Michael Keaton Batman. They had Jack Nicholson as Joker. Anyway, total.
Was Weird Al the director?
It's his movie, so probably. I don't remember. I mean, he's everything. He's the main character. We should just watch it someday in class. But all right. So another example of net change. You can have the velocity was, I don't know. Say I'll do this one. V naught minus gt, right? And here this is equal to dy dt, right? And so here I'm saying that v naught's the initial velocity, and g is, 9.8 meters per second squared, gravity, right? Gravitational constant. I'm saying t is in seconds, y is in meters. If I want to calculate how far you go from time 1 to time 2, I can do this. I can say y of t2 minus y of t1, which you could also call the change in y. Well, that's the integral from t1 to t2 of dy dt. dt, right? And, okay, but we know that dy dt, we're given that it is v naught minus gt, right? So you guys can do that integration. What is the antiderivative of v naught? V naught's a constant, right? So the antiderivative of v naught is just v naught times t. What's the antiderivative of minus gt? You guys told me a second ago the antiderivative of t was t squared over 2, right? This time there's no 2 to cancel, so it's just minus 1/2 gt squared, right? And then FTC II says I take all that and I evaluate from time 1 to time 2. And so, what's that? So you get v naught t2 minus 1/2 g t2 squared minus v naught t1 minus 1/2 g t1 squared. Okay, this becomes more interesting. This becomes more interesting, or more recognizable, if I make some adjustments here. Okay, so I say like, okay, so let t2 just be equal to t, which we're thinking of as the final time. All right, and let's let t1 to be equal to 0. All right. If I make those adjustments, just the same calculation I just did, but plug in those special choices, then what we have is that y of t minus y of 0 is equal to v naught t minus 1/2 gt squared, and that's 0. So in other words, what you got is that y of t is equal to y sub naught plus v naught t minus 1/2 gt squared if I use the notation y of 0 is y sub 0, as is commonly used in physics. And there you go, that's one of the kinematic equations. You're like, didn't we already do this? We did this before, but we did it where we did an indefinite integral and then we fit a constant. Did I fit a constant here? I mean, not really. I did the integral and I got a formula, and that's kind of it. Now I had to do the kind of sneaky thing of putting t2 equal to t and t1 equal to 0, but that's just poor planning on my part, you know? I could have integrated from 0 to t at the outset. But if I did that, then there's some other things I don't want to get into that today. Let's not muddy the waters. So, total change theorem. So I could keep doing more elementary examples of integrals, but I think we've done enough that you guys see what's going on. Am I right? So I think it would be more useful for you in the big... there's one other kind of example I need to do for you, though, because there's another kind of example that will catch you off guard. So we need to talk about piecewise defined functions. Piecewise functions, when we're integrating piecewise defined functions, we have to deal with the pieces, so to speak, you know. Aw, man. It's just trying to get away from me. Well, somebody's in trouble out there, I'll tell you that. I'm glad I'm not the receiving end of that.
Oh, outside.
Yeah, somebody's getting a talking to. See, I think this is why I could never be a police person.
Is that a movie?
Is it a movie? It's possible that they're watching a movie in the auditorium. Let's hope for that. So, example. So if we had f of x equal to, let's say, x squared for x less than minus 1 and e to the x for x greater than or equal to minus 1, right? And you were asked to integrate, say, from minus 2 to 0, f of x dx, what would you do? How do you integrate something like that? So you don't have one formula, right? So it's very simple, actually. You just have to be aware of how to do it. You have to break it up into pieces. And so here we do minus 2 to minus 1, f of x dx, right? Plus the integral from minus 1 to 0. F of x dx. So that's the integral. And now we can put specific formulas, right? Because between minus 2 and minus 1, we're dealing with x, which is less than minus 1, right? So the correct expression to put for that integral is x squared. And the other one, since x is larger than minus 1, we're in the e to the x case, yeah? And then we integrate, as we have previously. So the integral of x squared is what? 1/3 x cubed. I evaluate from minus 2 to minus 1. And then plus e to the x, going from minus 1 to 0 at the top, right? By FTC II. I'm applying it twice, one for each integral, right? So what do I got? I've got 1/3 of minus 1 cubed, right? Minus 1/3 of minus 2 cubed. Gotta watch the minuses on this one. Plus e to the 0 minus e to the minus 1. So that gives me a minus 1/3, and that gives me a minus 8/3, right? But there's a minus. I get plus 8/3 overall there, don't I? 8 minus 1, 7/3. So it looks like I've got 7/3 plus 1 minus, well, 1 over e, if you like. Whatever, however you want to write that, but there you go. I guess I could write that as 10/3 minus 1 over e. Anyway, you could punch it in your calculator and get a decimal number there if you like. So these piecewise defined examples, they're trickier when you don't see them coming. All right, there are functions which are piecewise defined, but they're kind of clandestinely so. And the main one I think about, of course, is like absolute value. So why do we care about absolute value anyway? So let me talk about an application to integration here. So I've talked about the fact that, you know, if we have the function, right, and it looks like this and like that, right? And suppose this is, you know, here's A and here's B, whatever. And so if we calculate the integral from a to b, and this is y equals f of x, of course. So if we calculate the integral from a to b, what are we calculating? It gives us the signed area, right? Bounded by y equals f of x for a less than or equal to x less than or equal to b. What if I don't want the signed area? What if I want the actual area bounded? How can I calculate the area bounded? You know, suppose I want to count this. I mean, this and this are already positive, right? But this guy in the middle, you know, I really want to think about flipping that up here. Like that, right? So if I could have a function that looked like the same but reflects the negative parts like that, see that right there is y equals absolute value of f of x. That's what that is. If we look at the absolute value of a function, it turns the negatives to positives, right? So like the integral from a to b of the absolute value of f of x dx, this is actually going to give us the area bounded by y equals f of x and x-axis, to be more precise, for a less than or equal to x less than or equal to b. So an example, find area bounded by y equals to x squared minus 4 for, well, x squared minus 1 rather. Minus 2 less than or equal to x less than or equal to 2. So to understand this problem, I really need to make a graph. What are we looking at here? This has plus and minus 1 as x-intercepts. It's got minus 1 as the y-intercept. This graph is something like this. Right? This is y. That factors as x plus 1 times x minus 1, right? Difference of squares. So if I were to draw a picture of what we're doing, trying to find from like, minus 2 to plus 2, right? So we've got like, we're trying to get this area and this area and also this middle area, right? We need all of those. So the area, integral from minus 2 to 2 of the absolute value of x squared minus 1 dx. And so the most straightforward, way to do this is just to admit that there are three cases, right? Minus 2 to minus 1, right? And in minus 2 to minus 1, what's the value of the function? It's positive there, right? We're in here. So that, we just put x squared minus 1. And then plus the integral from minus 1 to 1 of 1 minus x squared. See, the absolute value, I'll write it up here. This case right here, the absolute value of x squared minus 1 equals to minus x squared minus 1 equals to 1 minus x squared for minus 1 less than or equal to x less than or equal to 1. So I put a minus sign in there to make it negative turn to positive. I mean, that's the absolute value. It's already there. And then, of course, plus the integral from 1 to 2 of x squared minus 1 dx. Now, there's a way to be lazier here. And let's be lazy since we can. There's a symmetry in this problem that we can exploit, right? If you look at this, the rightmost part of the area and the leftmost part of the area, they're the same shape, right? This graph it's an even function. What happens to the left happens to the right in the same way. There's a symmetry between positive and negative here. So what I'm trying to say is we don't have to calculate three integrals. We can actually just calculate this and realize it's equal to that. So instead of we'll just calculate, I prefer this one because it's got less minuses. And so we're just going to double up on that one, 2. And then what's the antiderivative there? We got what, 1/3 x cubed minus x, right? And we evaluate from 1 to 2. So that should take care of the n pieces. The minus 1 to 1, what's that? Plus, what's the antiderivative there? X minus 1/3 x cubed, right? Evaluated from minus 1 to 1. And then we just need to plug in the numbers and be careful, right? So like, we've got 2 times 8/3 minus 2 minus 2 times 1/3 minus 1. That's just the first in orange one. And then this one plus 1 minus 1/3 minus 1 minus 1/3 of minus 1 cubed. You gotta be super careful with the minuses. It's so easy to make a mistake on those. Let's see here. 8/3 minus 2. That's 8/3 minus 6/3, so that's 2/3. I got 4/3 from the first one. 1/3 minus 1 is minus 2/3. So that's also plus 4/3. That's funny. So then plus 2/3. And let's see this one. That's minus 1 plus 1/3. That's minus 2/3. Is again plus 2/3. So if I haven't messed up the arithmetic, 4 plus 4 is 8, plus 2 is 10, plus 12, 12 over 3, 4. Wow, nice answer. 4. Huh, cool. So what makes this problem hard? Is it the calculus? Not really. I think the hard part here is understanding that we have to look at absolute value, draw the graph, and realize that you have to, break it up into the places where it switches from positive to negative. That's what makes this kind of problem trickier. This one is in some sense simpler because I'm just kind of like yelling at you, hey, here's these two cases. This one's x squared, this one's e to the x, right? This also is case-wise, piecewise kind of thing, but you have to figure out for yourself in this kind of problem where to switch the negative to a positive, So. Would you guys like to see another example of these? Yeah, okay. Try to work something a little bit simpler. Find area bounded by y equals to absolute value of 3x minus 5 for 0 less than or equal to x less than or equal to 2. All right, so how to graph something like this? Like what I would do, well, it's absolute value, right? So let's just kind of make a picture of it first. Where is it 0? It's 0 when 3x is equal to 5, right? This is where it's 0. So 5/3, So here's 0. Let's say this is 2. This is 1. So 5/3 is here-ish, right? So this thing should look something like, very crudely speaking, not to scale by any means, right? Like what is, for the sake of discussion, what is this y-intercept? The y-intercept, put x equal to 0, the y-intercept is 5, right? This point right here is 5/3. So just to emphasize what's going on, you've got for this line, y equals 5 minus 3x, right? And for the other line, you've got